Lecture 9. We will be talking about the equilibriums of slightly soluble ionic compounds as well as complex ions. Alright, so we're going to look at chapter 19.2, the equilibrium of slightly soluble ionic compounds. We'll be looking at the equilibrium systems that deal with the solubility of ionic compounds. So recall in chapter 13 that most solutes, even those called soluble, have a limited solubility in a particular solvent. In a saturated solution of a particular temperature, equilibrium exists between dissolved and undissolved solute. Slightly soluble ionic compounds, which we've been calling insoluble, reach equilibrium with very little solute dissolved. We will assume that, like a soluble ionic compound that does dissolve, dissociates completely into ions. So for slightly soluble ionic compounds, equilibrium exists between the solid solute and aqueous ions. So let's take a look at an example. We have lead 2 fluoride, solid, goes to lead, aqueous ion, to 2 fluorine ions. Now let's write the reactant quotient for this. So we get the reactant quotient of the ions, which are products, all over lead 2 fluoride. Now one thing we have to remember is that lead 2 fluoride is a pure solid, so it's going to equal to 1. So we actually get QSP from our QC when our lead 2 fluoride is equal to 1, and we have just our ions, our lead and our fluorine. Now, what is QSP? QSP is known as ion product expression. So QSP again is our ion product expression. So when the solution is saturated, the numerical value QSP attains a constant value called the solubility product constant, KSP. The KSP for lead 2 fluoride at 25 Celsius, for example, is 3.6 times 10 to the minus 8. Like other equilibrium constants, KSP depends only on the temperature and not on the individual ion concentrations. So when we're writing the ion product expression, we use M, the subscript XQ equals P Mn plus our Q of X2 minus. So what we did is we just broke apart our ionic and we created a new ions. So our QSP is going to equal, as we know, our ions. And don't forget that coefficient becomes a subscript. And it's also going to equal to our KSP. Now there is a special case, and that special case is with metal sulfides. So the aqueous equilibrium of the metal sulfides have a special form for the ion product expression. The sulfide ion, S2-, is so basic that it reacts completely with water to form the hydrogen sulfide ion, HS- and hydroxide, which we can see here. Although S2- is not stable in water, we can think of the dissociation process as the sum of 2 steps, with S2- formed in the first and consumed immediately in the second. So let's do an example with manganese 2 sulfide. So the first thing we're going to do is we're going to take manganese 2 sulfide and we're going to create its ions. So we get sulfide and manganese. Then the next step is we're going to now consume the sulfide ion. So once we write out the reaction, we can now get rid of what's similar. So we notice we have 2 sulfides, so we can cross that out. Now we can bring everything down. So we are given manganese sulfide plus water forms HS- plus hydroxide plus our manganese ion. Now when we write this as our KSP, we're going to get the manganese ion, HS negative, and hydroxide. Remember that the manganese sulfide solid is going to be a solid and it's pure, so we cannot write that into our KSP. And water, because it's a pure solvent, we will not be writing that down as well. Let's try another example. If I gave you magnesium carbonate, what should you first do? You're going to break it up into its ions, which you can see here. So I have my magnesium ion and my carbonate ion. Now, then I can now break it up into my KSP. So that's what I'm going to do. And I get my KSP is equal to my magnesium ion and my carbonate ion. And just remember, KSP is known as our solubility product constant. Now let me give you another example. I'm going to give you silver sulfide. So the first thing you need to do is break these apart into its ions. And we get 2 silver ions plus sulfide. And again, we need to break apart sulfide. So let's do that. And I get sulfide ion with water creates HS negative and hydroxide. Now I'm going to cancel out the sulfide and see what I have left over. And I have my silver sulfide, water, my hydrogen sulfide negative, my hydroxide, and 2 silver ions. Now I'm going to do my KSP, and my KSP gives me my products. Alright, so how do we find KSP without looking in Appendix C? So if I give you lead 2 sulfate, it's soluble in water at 25 Celsius, and it's 4.25 times 10 to the minus 3 grams over 100 milliliters of solution, what is the KSP of lead 2 sulfate? Well, the first thing you want to do is write the equation and the ion product KSP expression. So let's do that. So we get our equation and our ion product expression. Now we're going to convert the solubility to molar solubility. Let's go. And then I get 1.40 times 10 to the minus 4 molarity. So I just took the grams and I multiplied 10 to the third milliliters to get our liters. And then I took the grams, used the molar mass of lead 2 sulfate, and I was able to get my molarity. Now I want to find the molarities of my ions. So what I need to do is I need to actually look at this reaction and go, okay, if I have 1.40 times 10 to the 4th molarity, I also would have 1.40 times 10 to the minus 4 molarity for lead, as well as for the sulfate, because it's a 1 to 1 to 1 reaction. So now that I have the molarities of the ions, I can now find the KSP. So I'm going to look at my KSP equation and I'm going to plug in the molarities of the ions to that equation. So when I do that, I get 1.96 times 10 to the minus 8. Remember, with anything that is an equilibrium constant, you never put a molarity to it. Now let's try another problem. So if you were given lead fluoride with pure water at 25 Celsius, the solubility is found to be 0.64 grams over 1 liter. Now I want you to calculate the KSP for lead fluoride. Now what's the first thing you need to do? Write the equation and find the KSP expression. So let's do that. So I get lead fluoride becomes lead ion and 2 fluoride ions. So my KSP is my lead and my fluorine ion. And don't forget that 2 from the coefficient now becomes a subscript. Now I'm going to convert the solubility to molar solubility. So after I do the equation, pretty much I need to take the grams, get into moles. I'm already at 1 liter. I get 2.6 times 10 to the minus 3 molarity of lead fluoride. Alright, so next thing I need to do is find the molarities of the ions. So here we go. Alright, so we know that the lead fluoride is going to equal to the lead ion, so we're going to get the same molarity. Now for the lead fluoride going into fluorine, we know we have 2 more fluorines, so we need to double our lead fluorine 2. So if this confuses you, just remember about doing a mole to mole ratio. So when you have the 2.6 times 10 to the minus 3 of PbF2. You have 1 mole of PbF2 for every 2 moles of fluorine ion. So that's how we get the 5.2 times 10 to the minus 3. Now we can find our KSP now that we have the molarities. Alright, so I plugged it in to my KSP. So lead ion was 2.6 times 10 to the minus 3. The fluorine ion was 5.2 times 10 to the minus 3. Again, do not forget you need to square this to get me my KSP of 7.0 times 10 to the minus 8. Now that we know how to solve for KSP, how do we determine the solubility? Alright, so we're going to calculate the molar solubility of calcium hydroxide in water given that the KSP is 6.5 times 10 to the minus 6. Sometimes you can find the KSP in Appendix C, or I'll be giving it to you. Now, what's the first thing you should always do? Write the equation and find the ion product expression. So here we go. So we get calcium hydroxide forms calcium ion plus 2 hydroxides, and our KSP is going to be our calcium ion with hydroxide, and don't forget that 2 for the subscript. Now we're going to draw a reaction table. This is going to help us figure out what we have and what we don't have. Alright, so the first thing we need to know is we really don't have anything with calcium hydroxide. The reason why is because we are breaking it apart into ions. Now for calcium ion, we start with 0, and the hydroxide, we start with 0. Now for the change, we actually get a change because we actually get calcium solubility, and we get 2 solubilities of hydroxide because it has a coefficient of 2. So let's see what happens at equilibrium. We have 1s for calcium, and for hydroxide we have 2s. So let's fill this in with our KSP. So we know our KSP is equal to our calcium ion and our hydroxide ion, 2. And we're going to fill those in with s's. So we have an s for calcium ion, and we have 2s for the hydroxide ion. And this actually gives us, so when we square root this, we get 4s squared, and then we times it by the s, and we get 4s cubed. Alright, and then we just need to find the molar solubility of each of these. So we're going to find the S while we plug in the KSP. So we have our KSP, 6.5 times 10 to the minus 6 is equal to our 4s cubed. Now the first thing I'm going to do is divide by 4. So I have 6.5 times 10 to the minus 6 all over 4 is equal to s cubed. And then I'm going to cube each side to give me s, our solubility, is equal to 1.2 times 10 to the minus 2 molar. So that means our calcium, since it was equal to S, is equal to 1.2 times 10 to the minus 2 molar. And our hydroxide, which was equal to 2S, is 2.4 times 10 to the minus 2 molar. So that's how we were able to get our KSP. So if we wanted to work backwards, we can. So let's talk about factors that affect the solubility. Well, the first thing we need to talk about is Le Chatelier's principle. Sorry, I'm not really good with my French. But the concept is, if a change occurs to any factor that affects a system at equilibrium, the equilibrium will shift so as to counteract the effect of the change. So if I add heat to the reactant, it's going to shift right. If I add heat to the product, it's going to shift left. This concept we saw in Chem 100. Now let's go into other factors that are going to affect the solubility. So the first factor that affects solubility is the common ion effect. So if I give you an ion, so I'm just going to draw just a simple one. And we break it up to its ions. So here's an ion, we broke it up into the, here's a compound, we broke it up into its ions. Now let's talk about the ion's concentration. So if we increase the ion's concentration, let's say we increase the M positive, for example, what's going to happen? So what happens is the ion concentration will increase. Normally we're always focusing on one ion, the other one is normally neutral, and the equilibrium is going to shift to the left. So it's going to go this way. And the solubility is going to decrease. Well, what happens if we decrease the ion concentration? So when we decrease the ion concentration, the equilibrium shifts right, and the solubility increases. So let's take a look at a few examples to figure this out. Alright, so I give you calcium carbonate. The first thing you're going to do is you're going to break it up into its ions, so you get calcium 2 plus aqueous plus the carbonate, CO3 2 minus aqueous. Now, how about if we add in some sodium carbonate? Well, when we add in sodium carbonate, we're actually increasing the carbonate right here. So we're adding more of the carbonate ion. Calcium 2 plus right here, if you remember, is a neutral because it's from a strong base. So right now we're going to increase the ion concentration. So when we increase the ion concentration, what's going to happen? Well, the reaction is going to shift left. So we're going to go left, and solubility is going to decrease. So now that we're at equilibrium and it has been reestablished, well, what happened to that calcium 2 plus? We know it's neutral, but because we increased the carbonate, we actually decreased the calcium. So KSP is equal to the calcium 2 plus and the carbonate 3 2 minus. So again, we increased the carbonate and we decreased the calcium for us to reestablish equilibrium. So just always remember, if one ion goes up, the other one has to go down. But we are focusing on the carbonate. Why? Because we added more of the carbonate to it. Now let's do an example of a problem that you might see on an exam. Alright, so what will be the solubility of calcium carbonate and 0.1 molar sodium carbonate? Well, the first thing you need to do is write out the equation and the ion product expression for the calcium carbonate. Alright, so we did this previously, the last problem I worked on. Okay, next thing you want to do is write a reaction table because you want to figure out what is going on. So here we go. Alright, so one thing we know is the calcium carbonate, nothing is going to happen with it. Now, we are adding in sodium carbonate. That means we're adding in more carbonate. So the initial is 0 for the calcium, but we're adding in 0.10 molar of extra carbonate. Now the change is plus molar solubility, and the carbonate is plus molar solubility to give us S for the calcium and 0.10 molar plus S for the molar solubility for carbonate. Now, just like with the weak acids and weak bases, when we look at 0.1 molar, what we need to look at is we need to compare it against the KSP. Well, the KSP for calcium carbonate is equal to 3.3 times 10 to the minus 8. Because KSP is so small compared to the 0.10 molar, I can actually just cross out the plus S. So let's set up this problem. So I'm plugging in the molar solubilities for the ions. So for calcium, I have S. For carbonate, I have 0.10 molar because 0.10 molar is so much greater than the KSP. So now I just need to divide 0.1 on both ends to get me S is equal to 3.3 times 10 to the minus 8 molar. And that's all I need to do for this type of problem. Now let's talk about another effect that can happen, the pH effect. So let's do this by an example. If I give you calcium carbonate again, I'm going to break it up into its ions, the calcium and the carbonate. What do I know about calcium? Well, calcium is going to be neutral. Why? Because it comes from a strong base. Now the carbonate we know is going to be a weak base because it comes from a weak acid, HCO3 minus. So the rule is, if a slightly soluble ionic compound contains the anion of a weak acid, for example carbonate, the addition of hydronium from a strong acid increases its solubility. Now let's do a few examples on this. So if I give you manganese hydroxide, which is a solid, we're going to break it up into its ions, so manganese 2 plus aqueous plus 2OH minus aqueous. Alright, first thing we know is manganese is neutral because it comes from a transition metal, so it's one of our neutral ones. And the hydroxide is the anion of water, which is a weak acid. So that means hydroxide is going to be our weak base. So because we have a weak base, that means we have an increase of solubility. Alright, so if we lower our pH, as in we add in more hydronium, our OH negative, our hydroxide, is going to decrease in value. That means the reaction shifts right. That causes our solubility to increase it. So if you remember from our rules previously, when the ion concentration increases, the equilibrium shifts left, and we have a solubility that decreases, or when the ions increase, the equilibrium shifts right, and the solubility increases. We're just playing back on that. So we're going to work backwards. So again, if I have a weak base, that is an anion of a weak acid, I know the solubility will increase. If my solubility increases, that means the concentration of that ion had to decrease, and the equilibrium needs to shift to the right. Now, what happens when we add in a base, so a higher pH? That means the hydroxide is going to increase because we're adding more hydroxide to it, and the reaction is going to shift to the left, so it's going left, and the solubility will decrease. So again, when we increase the pH, we are increasing the base. So our ion concentration is increasing. That means we are shifting to the left and our solubility will decrease. Let's do one more example. Alright, so let's do iron 2 sulfide. So iron 2 sulfide is a solid. Alright, so we get the ion of iron and the ion of the sulfur to give us sulfide. Now remember, with sulfide, we need to break it apart again. S2 minus aqueous plus water, liquid, gives us HSS negative aqueous plus hydroxide negative to give us a full reaction of FeS plus water and gives us Fe2 plus aqueous plus HS negative aqueous plus hydroxide aqueous. So because we have two anions that both came from water, which was a weak acid, these are weak bases, that means by the definition, if we increase the pH, when we increase the hydronium, we are decreasing, we have a lower pH. That means our solubility is increasing. We are shifting to the right, so our shift, and our ion concentration is decreasing. Now, if we have a pH that's higher, so we're adding in more, let's say, hydroxide, our solubility is going down. We're shifting to the left, and our ion concentration is increasing. So just from knowing that simple rule about having a weak base in the product, we know if we lower our pH, we are going to have an increase of solubility. We're shifting to the right, and our ion concentration will decrease. Now, if we add in a higher pH, like hydroxide, we are going to lower our solubility. We are going to shift to the left, and our ion concentration will increase. Now, one thing I want to make sure you understand, amphoteric hydroxides, remember amphoteric means able to act as either an acid or a base. They're soluble at low pH and high pH, but are insoluble at neutral pH, pH of 7. Examples of this is aluminum hydroxide, chromium 3 hydroxide, zinc hydroxide, and tin 2 hydroxide. Alright, so now we're at chapter 19.4, complex ions. A complex ion consists of a central metal ion covalently bounded to two or more anions or molecules called ligands. So how does this look? So we have an M, X plus, should be an X, plus NLZ minus goes into MLN X minus Z. So this gives us our complex ion right here. And this right here is known as our ligand. So this was our So ligand can be an anion, hydroxide, or neutral molecules with lone pairs. For example, ammonia. But because most complex ions deals with water, we actually have to form a new constant known as the formation constant, which we'll see in the next video.